Okay, let's take a look at an example on potential divider principle. So we have an EMF E with 0 internal resistance connected to resistance R1 and R2. So one way to derive the potential difference across R1 is certainly to do the steps of calculating the current and then deriving VAC. The other way is just right away to look at the total resistance. So in this case, I will say R1 plus R2 is actually directly proportional to the EMF E, while R1 is directly proportional to the EMF, to the potential difference VAC. So by dividing these two equations and making VAC the subject, you can right away arrive at this. Similarly, in the same vein, if you want to find the potential difference across VCB, we can do likewise. The only difference is that R2 is directly proportional now to VCB. And from there, we again can derive this expression. So this is a very quick way of actually calculating potential difference without having the need to calculate the current. So let us take a look at some examples. One example that we could look at is this. So these two resistance is in parallel. So R effective in this case will work out to be 5 ohm because 1 over R effective is 1 over 10 plus 1 over 10. So it means, so therefore from here, we can conclude to say that total of 55 ohm is directly proportional to 6 volt. So the potential difference, say for example, across the 50 ohm resistor, which is your VBC, and you can divide the two and calculate it, where VBC will now be equal to 6 volt divided by 55 multiplied by 50. Okay, another example that we look at is 4 kilo ohm and 1 kilo ohm. So it should be quite straightforward. So the potential difference across here will be 105 multiplied by 25, while the potential difference across this resistor will be 4 over 5 multiplied by 25 volt. Let's take a look at a very popular question on the specific network of resistor. So this is actually the 5 resistors that's always tested in exam. So you will be able to see that we have a resistors layout as such. And what we have done here is to label the points. By labeling the points, it guides you to draw the resistors in an easier manner for you to interpret. So in this case, point A actually branches into resistor 1 and 4. So I will actually do this drawing first. And point A will go to point C. And you can see that the A will go to B, which is here. And B to C will then has a resistor number 2 here, while B to D has resistor number 5 here, while C to D has resistor number 3. So from this circuit, we can actually be able to draw to a network like that, which makes it easier for us to interpret. So if in the exam questions, there's a couple of questions that could be asked. So one question is that they want to know the R effective across A and D. Okay, this is one possibility, which is the most asked question. So if all the resistors are all identical, then the potential difference, so the current will come in here and it will flows out here. Current will come in here and flows out here. Of course, this is the part that we'll be explaining as to why there's no current flow. The reason is because this is exactly symmetrical to this part, which means the potential difference across here and the potential difference across here is the same. The potential difference across here and across here is the same, which means VB must be equal to VC. Hence, because of that, there will be no current that flow in resistor 2. So the way to calculate the resistor, the R effective across A and D will be pretty straightforward because it's good as taking this out, which means you can sum up both the resistors on the top and sum up both the resistor below, and then you can use the formula for calculating the R effective for resistors connected in parallel. Okay, let's take a look at other questions. Say if they change, they say they want the R effective across C and B. Okay, If now you want the current to be coming in from here, which means in this case, I'm going to work this out. If the current is coming in from here and flowing out from here. So in this case, you will have 3 sets of resistors actually in parallel. One will comprises 3 and 5, the second just 2, and the next one will be 4 and 1. So this should be quite easy to calculate because you can just deploy the formula for calculating effective resistance for resistors connected in parallel. Okay, let's take a look at another one. Say we want to connect, we want to know the R effective across, say, C and D. Okay. So in this case, the current will flow in here and flow out here. All right. So again, shouldn't be an issue. So the first part that we need to do is to sum this up. Okay. Sum 1 and 4. And 1 and 4 is connected in parallel to 2. So you can work out the R effective for this. And after that, you can add this up. All right. So because this will be in series to this R effective here. And finally, once you have the R effective of all these, they are actually connected in parallel to resistor number 3.